My name is Alex Miller. I founded a company called Capnion to produce the type of data privacy software I'm about to show you right now. To look ahead, I'm going to show you a problem and an opportunity wrapped up in each other, hopefully give you a sense of why they're important, and demonstrate a solution to you. To get started, let's say someone handed you an encrypted spreadsheet. Depending on your organization, it's maybe a great thing that it's encrypted because if you lose it, you've minimized the harm to the public and the embarrassment for yourself. You're in a bit of a pickle now, though, because you might need to do some work on this data. In the past, maybe you would decrypt here to do your work, and in the process create a security liability. I'd like to show you a third way where you can leave the data encrypted and still get your work done. The problem and the opportunity here is keeping your data encrypted, and I'd like to show you a way to get to pure opportunity. Let me outline a little bit what you're looking at right now and what I'm going to show you. Here I'm working with Python and a Jupyter notebook. Just about everything I'll show you will be very familiar to the data science crowd, and in particular I'm going to use some fairly standard techniques at the end to accomplish a fuzzy deduping on this address column. I'd like to emphasize that it's really a selling point here that a lot of the code I'll show you may be very familiar to data scientists in your organization. And what I'm telling you is a really great opportunity is that your people can continue using their skills in the same way without a whole lot of interruption. And the Capnion software will allow you to accomplish something doing that work directly on the encrypted data that has really powerful ramifications for your information security. Now let's get into the details. This first block of code is oriented towards defining this similarity function at the end. I've got an example here. It's pretty intuitive what the function does. Cook and cookies both contain the word cook. They're about half the same. They get a relatively high similarity score of 0.5. Tinus and Macedonia are not similar at all. They get a relatively low score of 0.083. I'm showing you this code here mostly just to show you that it's relatively simple. You can see, if you're familiar with Python, that everything's written in a way that it could operate on normal strings and not encrypted strings or anything fancy that Capnion developed, and I'm demonstrating this right here. I'm applying it to these words. Just to demonstrate that the magic trick I'm going to do maybe is actually a cool magic trick, if I were to just directly apply this bigram similarity function to the encrypted data I showed you above, I'm not seeing a whole lot, and I shouldn't expect to see a whole lot. If I have a good technique of encryption, whether the ciphertext is similar to another piece of ciphertext should have nothing at all to do with whatever I encrypted to get it. And that's pretty much what I'm seeing here. Now this is an important stopping point. This is where I pull in Capnion's code. And what follows, I'm not going to work with that encrypted data. I'm going to work with a new object that's defined in the code I'm importing here. This object is a bundle of the encrypted data and some information about how Python should interact with Capnion's API. The point of this object is that it looks like a string to Python. You can treat it like a string. You can do all the things you would normally do to a string. And the software on the back end is going to do the work of keeping you correct. After you've done all this work with these fake strings, if you were to decrypt, you're going to get the answer you would expect as if you'd done everything on the unencrypted data from the beginning. I'd like to stop briefly and zoom out to an organization-level view of what's going on and what Capnion is doing under the hood. The idea here is that you encrypt any kind of personal information you get right away. When you come to points in your data pipeline where you need to do work on that data, Capnion's API is supplying keys that can be used to do that work and nothing else. And in particular, they can do that work, but they cannot decrypt. Now let's look at this machine in action. First, I'm going to repeat my exercise from a moment ago, but this time I'm using Capnion software. I get a very different result this time. I can see that several of the rows of my spreadsheet are the same as that first row, and this is more reasonable. I'm seeing that the addresses are sometimes very similar, sometimes they're not very similar at all. I want to cheat a little bit. You know, you'd like to see that you're getting the right answer, so I happen to have the plain text. This is not what you would do in practice, but I just want to convince you that there's no sleight of hand here. So, when I look at these first few rows, it is true that the first and the second row of the spreadsheet are exactly the same address, 1 N Ogden AVE Avenue. So I got the right answer when I did my computation on the encrypted data. Just some more verification, I'm going to look at row 0, row 1, row 0, row 1 on both plain text and encrypted data. I get the same answer and the right answer. Then I'm going to do it for row 1 and 2. Once again, I get the same answer and the right answer. So I can compute things on the unencrypted data, I can compute things on the encrypted data, and I'm ending up in the same place if at the end I happen to have the ability to look at the original data set. This part at the end here is the data science part. I'm going to run dbscan. It's a clustering algorithm on the information I got from looking at the similarity between all the addresses in this list. A clustering algorithm is just something that takes a list of things and puts them into groups. So my output here, I'm going to look at my first non-trivial cluster. I'm going to output all the ciphertext addresses in that cluster. Right now, this looks like a lot of gobbledygook, right? But once again, I'm cheating a little bit. I have the plain text. What do I see when I examine that cluster I computed on the encrypted data in the context of this cheat information about the plain text? I get something very reasonable. I picked out all these 1 North Ogden Avenues, and not only did I pick out the cases where they were identical, I even picked out some of these cases where I had N period instead of N, I had North instead of N period, I had Avenue instead of AVE. So this is not only a road to deduping the data set, I've even done a fuzzy deduping entirely on the encrypted data. And aside from my cheat access to the original data set, I was working only with keys supplied by Capnion's API that did not grant me any power to decrypt.